wave nature of the matter. As we have told that radiation has the dual nature, that means the wave particle nature. Now question arises that does the particle like protons, electrons, etc. also exhibit the wave-like character? It is reasonable to consider that nature is symmetrical, that is matter and the energy must have the symmetrical character. So if the radiation shows the dual aspects, should the matter. And on the basis of this, de Broglie proposes a bold hypothesis, and it is moving particle of matter should display the wave-like properties under the suitable condition. And on the basis of this hypothesis, it also proposes the wavelength associated with the moving particle is lambda equal to h by p, where h is the Planck's constant and p is the momentum of the particle. And by definition, momentum of the particle is given by mass into velocity. So this lambda, that is the wavelength of the wave associated with the particle, is h by mv. Here this wavelength lambda is the wavelength of matter wave, also called the de Broglie wavelength. If we draw a graph between the lambda and the momentum, so it is a graph in which if momentum increases, wavelength decreases, because lambda is inversely proportional to the p. That means if momentum increases, that means for same velocity, if mass increases, then this wavelength will decrease. And if mass decreases, then wavelength will increase. So we can conclude that for matter wave, lambda or the wavelength is so small to measure for the macroscopic objects, but in subatomic particle like photons and protons, the speed is very much higher. This shows the wave character of the particle in a significant and the measurable way. The formula which we have discussed, which will be important for the different numerical purposes. Number 1, energy of the photons is E equal to h nu, and this further can be written as hc by lambda. And momentum, here this E is energy and P is momentum, or we can say linear momentum. This momentum is E by C. This we have to remember. Second, for matter waves or the de Broglie waves, the wavelength is given by lambda equal to h by p, and p is momentum, so it can further be written as lambda equal to h by mv. Because the matter waves are generally appreciable for the subatomic particles which have very high speeds, so for these particles which is having the say charge q is the charge on moving particle, and suppose this charge is accelerated by a potential difference v. This charge q is generally written in SI unit as coulomb and potential difference in volts. Then the kinetic energy acquired by the charge q when accelerated through the potential difference v is given by k equal to q into v, which we already discussed in the chapter of electricity. And because formula of the kinetic energy is if mass of the particle is m and it acquired the velocity v, if it's starting from the zero speed, that means it is starting at a start, particle is at rest. In that case, the gain in the kinetic energy is half mv square and it will be equal to qv. Or further we can write this kinetic energy as, because momentum is written as mv and k kinetic energy is written as half mv square, it can further be written as p square by 2, m. That means square of the momentum divided by 2m. Here we multiply numerators and denominators by 2m by m. So in numerator it becomes m square v square, which is momentum square divided by 2m. So momentum can be written as 2mk. On taking the square root on the both sides, it will be root 2mk. So this is the relation between the momentum and the kinetic energy. Therefore, from the formula, this is the capital V. This is the potential difference. So from this formula, we can write P square by 2m. This is the kinetic energy, and kinetic energy is equal to P square by 2m. So it is equal to QV, and momentum P will be equal to 2m QV square root. So the wavelength of the wave associated with the moving particle, that is the matter wave or the de Broglie wavelength, is h by p, or we can write it as h by root 2mqv. Here h is the Planck's constant, m is the mass of the particle. Say particle is electron, then m will be 9.1 into 10 to the power minus 31 kilogram. Q is the charge on the particle, and V is the potential difference through which the particle is accelerated from rest. This formula can be further simplified for electron. If we take the particle which is electron, and this is the case of the photoelectric effect, then for electron, H will be a universal constant, that is 6.6 into 10 to the power minus 34 joule second. Mass of electron is 9.1 into 10 to the power minus 31 kilogram, and V is the potential difference through which electron get accelerated. That means it is the potential difference across cathode and anode. This cathode is the source of electrons, and it is kept at negative potential, and this anode is the positive plate which accelerates or attracts the electron generated by the cathode, and cathode get energy that is equal to QV. So substituting these values, and charge on the electron is 1.6 into 10 to the power minus 19 coulomb, and substituting these values in the formula, that is lambda equal to h by p or equal to h by root 2, mass of electron, charge of electron, and potential difference through which electron is accelerated, we get on simplification 12.27 by root V angstrom, or we can further write it as 1.227 by root V nanometer. So from this formula, we simplified our calculation in a lot way, because we have reduced the multiplication by directly using this formula. For example, if we take V equal to 100 volt, then lambda on simplification will become 1.227 divided by root 100, and on simplifying we will get it is 0.123 nanometer. Similarly, if we take potential difference is 120 volt through which electron is accelerated, then wavelength of the matter wave associated with the electron will be 1.227 divided by root 120, and it will be calculated as 0.112 nanometer. Fourth is 1 electron volt is the energy which is equal to 1.6 into 10 to the power minus 19 joule. This is the energy which electron acquired when accelerated through a potential difference of 1 volt. So if electron is accelerated through a potential difference of 1 volt, then energy acquired is the 1.6 into 10 to the power minus 19 joule. Next point is, if E is the energy per photon, that is equal to h nu, or we can say it is hc by lambda, and n is the number of photons emitted by the source per second. E is energy per photon and n is the number of photons emitted per second. Then we can say Ne, that means this is the total energy emitted per second. This implies that it is the power transmitted in the beam or radiation.